Hello everyone, this is lecture 22, double integrals in polar coordinates. In the past, we explored polar coordinates and saw that in certain situations, they simplify problems considerably. The same is true when it comes to integrations over plane regions. And in this lecture, we learn how to formulate double integrals in polar coordinates and how to change double integrals from Cartesian coordinate or rectangular coordinates to polar coordinates. So that is the idea of this lecture, and hopefully at the end of this lecture you could be able to recognize the format of double integral over polar rectangular regions, and you could be able to evaluate a double integral in polar coordinates by using an integrated integral, and you could be able to recognize the format of double integral over a general polar regions. And before we get into the technique of evaluating double integral in polar coordinates, I'm going to give you a motivation example on how sometimes it's necessary to move from rectangular coordinate system to polar coordinate system in evaluating double integrals. So in example 1, suppose we want to find the volume of the solid bounded by the paraboloid z equal to 9 minus x squared minus y squared in the xy plane. So in this figure, it shows a graph of the surface z equal to 9 minus x squared minus y squared. And this is the circular shape on the xy plane. So you could like to find the volume of the solid bounded by the paraboloid in the xy plane. So again, notice that the intersections of the paraboloid and the xy plane is the curve 9 minus x squared minus y squared equal to 0, or x squared plus y squared equal to 9. So the intersections of the paraboloid and the xy plane z equal to 0 in this case is the curve and 9 minus x squared minus y squared equal to 0, or x squared plus y squared equal to 9. So the regions of integrations is the disk of radius r in the xy plane, center at the origins, and it has the form x squared plus y squared equal to 9. And the regions of integrations can be written as, so the regions of integrations is r equal to the set of all the point x comma y such that y is between negative square root of 9 minus x squared and positive square root of 9 minus x squared, while x is bounded between negative 3 and 3. You know the regions of integrations is the disk of radius 3 in the xy plane center at the origins, but when you form the double integral of the function with respect to x and y, you have to write the limit of integration for each variable in this particular form. And you see that the region of integrations become unnecessarily complicated. Therefore, in this type of situation, it's good to manipulate region of integration so that it makes our calculations of double integral a little bit easier. We notice that the regions of integration is expressed in terms of Cartesian coordinate system. And what we can do is we can convert this into polar coordinate system. Alright, so what you notice is that instead of x squared plus y squared equal to 9, we can write this as r squared equal to 9, because that is the relationship between the Cartesian coordinate and polar coordinates. So what we can do is that we can convert to polar coordinate system. So here you have x squared plus y squared equal to 9. You can convert this into r squared equal to 9, because we notice that x is equal to r times cosine of theta, y equal to r times sine of theta, and from this lead to the fact that r squared is equal to x squared plus y squared, and therefore you have r squared equal to 9. And if you take the square root on both sides of the equation, you have r equal to 3, which is take the positive value because r is the radius, and radius is always going to be a non-negative number. So therefore, the regions of integrations in Cartesian coordinates can be converted into the region of integrations in polar coordinate system as follow. You have r now becomes r equal to all the point r comma theta such that r is bounded between 0 and 3, and theta is bounded between 0 and 2 pi. Why is it between 0 and 2 pi? Because the regions of integration is the whole disk. Therefore, theta runs from 0 to 2 pi. In addition to the regions of integrations, we can also rewrite the surface in terms of polar coordinate system. That is, instead of z equal to 9 minus x squared minus y squared, we can rewrite that z is equal to 9 minus r squared. And the regions of integrations, again, instead of the regions of x comma y, such that x squared plus y squared less than or equal to 9, we can rewrite this as all the point r comma theta, such that r is between 0 and 3. So that is the motivations to give us the idea why sometimes we need to move from one coordinate system to another coordinate system. Now, the example you just see, or the regions of integrations in the problem, is an example of polar rectangle. So in polar coordinate system, the regions of integrations has the form. So regions of integrations R now has the form. It's the setup on the point r comma theta, such that r is bounded by a and b, where a has to be a non-negative number, and theta is bounded between alpha and beta, where a, b, alpha, and beta are constant. And that beta minus alpha has to be less than or equal to 2 pi. So some of the polar rectangle that you may encounter in this type of problem is that it may have this type of regions where r is bounded between 0 and b, while theta is bounded between 0 and pi over 2. Or it can have this type of regions, again, r is bounded between 0 and b, and theta is bounded between alpha and beta. For this particular example, when you look at the interval of r, you're going to draw a ray like this, starting from the origins to the boundary of the regions, and it's intersect here at this point to indicate that the lowest point that r can get to is 0, and the farthest point that r can get to is b. And for theta, you're going to draw an arc starting from the smaller angle to the bigger angle. Now, similarly, for this regions, you're going to draw a ray starting from the smaller radius to the bigger radius. And in this case, r is bounded between a and b. And for theta, you're going to draw an arc starting from the smaller angle to the bigger angle. And you're going to get theta, again, it's between alpha and beta. And the value of a, b, alpha, and beta will be determined in detail, depends on the problem. So what about the double integral? It's very tempting for us to just make the change in variable and rewrite it instead of dy dx or dx dy into dr and d theta or d theta and dr. Which is true in a lot of cases. However, there is a lot of missing component when we do just that. That's the reason that I have to rederive the double integral for polar coordinate system. So the goal is to evaluate the integral of the form, the double integral of the function f of xy, dA over a region or over a domain D in the xy plane, where f is the continuous functions on the polar rectangle R. So here is continuous function on the polar rectangle R. Now, our approach is very similar to what we did in the last lecture, is that we're going to subdivide the interval from a to b into m subintervals of equal length. So what we're going to do is subdivide the interval from a to b into m subintervals of equal length. And the length is calculated as delta r equal to b minus a divided by capital M. Now let's take a look at this figure. You have a polar rectangle, and you have the interval r going from a to r equal to b. And you're going to subdivide the interval from a to b into m subinterval of equal length, and the length is written as delta r. Now similarly, we're going to subdivide the interval of theta from alpha to beta into little m subintervals of equal length. For delta theta is equal to beta minus alpha divided by little m. So here you can see the rays that divide the regions into smaller thetas. For theta here is running from theta equal to alpha to theta equal to beta. They are subdivided into m subintervals of equal length. For the length is going to be delta theta. The arcs and rays divide the regions R into capital M times little m polar rectangles that we number in the convenient way from k equal to 1 to k equal to n. The area of kth rectangle is denoted as delta capital A sub k, as follow delta capital A sub k. which is again the area of the k rectangles. Now we're going to name the point on this rectangle as rk star, comma delta k star. We let this point be the polar coordinate of the arbitrary point in that rectangle. So if f is continuous on R, the volume of the solid regions below the surface z equal to f of xy and above the regions may be computed with Riemann sums, as you can see in the last lecture. At this point, you can evaluate the Riemann sum using the ordinary rectangular coordinate as we did in the last lecture, or in this lecture, we can evaluate the Riemann sum using the polar rectangles. Consider the box whose base is the kth polar rectangles and whose height is the function value. So consider the box whose base is the kth polar rectangle and whose height is the function value f of xk star, yk star. And we still use the idea of x and y, but we're going to convert that later to r and theta. But because remember that x is equal to r times cosine of theta, and y is equal to r times sine of theta. So the volume can be calculated as, so v sub k is equal to delta aik times f of xk star, comma yk star. Now this is the volume of just one box, the volume of just the kth box. Therefore, the volume of the solid regions beneath the surface z equal to f of x with a base r is approximately equal to. So now the volume of the solid regions beneath the surface z equal to f of xy with a base r is approximately, v is approximately equal to the summations of f of xk star, comma yk star times delta ak for k going from 1 to n. So this approximations to the volume is the Riemann sum. So let me note that is the Riemann sum. For n in this case is equal to capital M times little m, and this is the number of polar rectangles. And if we want to increase the accuracy of the approximations of the volume, what we can do is we increase the number of polar rectangles we use in the approximations. We increase that to infinity. Okay, so to increase the accuracy of the approximations, we do. So now instead of the approximation notations, we're going to use the equal sign. So v is equal to the limits of the summations for k going from 1 to n of f of x k star, comma y k star times delta a k for n going to infinity. Now instead of the notations in Cartesian coordinate, I'm going to convert that into polar coordinate system. And remember I mentioned earlier that x is equal to r times cosine of theta and y is equal to r times sine of theta. So instead of this limit, we're going to obtain limit as n go to infinity of the summations for k going from 1 to n of f of r k star times cosine of theta k star, comma r k star times sine of theta r k star times delta ak. Now the next step is to express delta ak in terms of delta r and delta theta. So this figure shows the kth polar rectangle with an area of delta ak. So the point of considerations in this case no longer xk, comma yk. Now we have the point rk star and theta k star. The idea is to calculate this delta ak in terms of delta r and delta theta. So this arc is delta theta, and this ray represents the length delta r. Delta ak can be evaluated by calculating the area of the outer sector minus the area of inner sector. So that is the area of the outer sector minus the area of the inner sector, and we're going to get the area of this region. And we call that the area of the sector is given as follows. The area is equal to 1/2 r squared times theta. So in this case, what we do is we calculate the area of the outer sector. minus the area of the inner sector, and again we're going to obtain the area of this region. For the inner sector, the length is calculated as rk star minus delta r divided by 2. And for the outer arc, the polar rectangle has the radius of the form rk star plus delta r divided by 2. Okay, so we have this value because of the way we choose the point rk and delta k. So again, I want to reiterate that the point rk delta k in polar coordinates is chosen so that the outer arc of the polar rectangle has the radius of rk plus delta r divided by 2, and the inner arc has the radius of rk minus delta r divided by 2. Now, the area of the polar rectangle is calculated using this formula, that is the area of the outer sector minus the area of the inner sector. And the area of the sector is calculated using this formula, 1/2 r squared times theta. Now we're going to plug in that formula of area of sector into this formula as follow. So again, delta AK is equal to the area of outer sector minus the area of inner sector. And the area of the outer sector has the form 1/2 times r squared times theta. Now r, the radius in this case, has the form rk star plus delta r divided by 2 altogether square times delta theta minus the area of the inner sector, and it has the form 1/2 times rk star minus delta r divided by 2 square times delta theta. So 1/2 delta theta is a common factor. You're going to factor that out. So 1/2 times delta theta, and you're left with rk star plus delta r divided by 2 square minus rk star minus delta r divided by 2 square. Now this is the difference of 2 square. We're going to evaluate the expressions inside the brackets as. So you're going to have rk star plus delta r divided by 2 minus rk star plus delta r divided by 2 times rk star plus delta r divided by 2 plus rk star minus delta r divided by 2. So we're going to simplify a little bit here. So rk star, negative rk star cancel out, and delta r over 2 minus delta r over 2 cancel out. And you get 1/2 delta theta times delta r from these calculations times 2 rk star from these calculations. Now the 2 cancel out, and you're left with delta AK is equal to rk times delta r times delta theta. So it's not as straightforward when you calculate the area of the polar rectangles. It's not direct translations from delta x delta y to delta r delta theta. There is an extra component, in this case is r sub k. Instead of the Riemann sum we see earlier, that is the limits of the summations for k going from 1 to n of f of r k star times cosine theta k star, comma r k star times psi of theta k star times delta AK for n go to infinity. We're going to see the limits now become limit as n go to infinity of the summation for k going from 1 to n of f of r k star times cosine of theta k star, comma r k star times psi of theta k star. And we're going to replace delta AK by rk times delta r times delta theta. So you have rk star times delta r times delta theta. Now instead of writing the limit of the Riemann sum, what we're going to do is we're going to change this into a double integral. And this again can be written as the double integral of f of x, y, delta a over a region R. This is equal to f of r cosine of theta, comma r times psi of theta times r dr d theta over the region R. And that is the double integral in polar coordinate system. Now we're going to put this into a theorem. And this theorem is the idea of change of variables for double integral over polar rectangle regions. So let f be continuous on the region R in the xy plane expressed in the polar coordinate as r equal to the setup on the point r theta such that r is between a and b and theta is between alpha and beta. Then f is integrable over r, and the double integral of f over r is given as, so the double integral of the function f of xy dA over the region r can be converted into the double integral of the form f of r times cosine of theta, comma r times sine of theta, times r dr d theta, for r going from a to b and theta going from alpha to beta. Now with this information, we're going to go back to the motivation example at the beginning and evaluate the volume bounded by the surface in the xy plane using the double integral over polar rectangle regions. So again, you want to find the volume of the solid bounded by the paraboloid of this form z equal to 9 minus x squared minus y squared in the xy plane. The first thing we need to convert from rectangular coordinates to polar coordinates is rewrite the surface. So instead of z equal to 9 minus x squared minus y squared, now we have that z becomes 9 minus r squared. Now we need to convert x and y into r and theta. We have seen this earlier already. So if this is the regions on the xy plane, this is the regions of integrations. You draw a ray from the lowest point to the highest point, and r going from 0 to 3. Then you're going to draw an arc starting from the smaller angle to the bigger angle. In this case, theta going from 0 to 2 pi. So the regions of considerations now becomes r of theta for r going from 0 to 3, and theta is between 0 and 2 pi. Now the volume becomes the double integral of the surface. The surface in this case written in polar coordinate system is 9 minus r squared times r, which is an extra component of the double integral in a polar coordinate system. And then you evaluate the integral with respect to r and with respect to theta. So this is the iterative integral for volume. For r going from 0 to 3 and theta going from 0 to 2 pi. So now you evaluate the double integral with respect to r and with respect to theta, but the inner integral is with respect to r first. Right. We evaluate the inner integral. You can either use the integration by substitutions, or you just basically manipulate the integrand by distribute r into the parentheses as follows. So you have the integral from 0 to 2 pi. Have another integral here from 0 to 3. We're going to distribute r into the parentheses. You get 9r minus r cubed dr d theta. So the antiderivative of 9r and minus r cubed with respect to r is 9 times 1/2 r squared minus 1/4 r cubed to the 4th. Evaluate at 0 and 3 d theta. So you get the integral from 0 to 2 pi of 9 over 2, 3 squared minus 0 squared minus 1/4 times 3 to the 4th minus 0 to the 4th d theta. If we do the calculations correctly, this expression is going to give us 81 over 4 d theta. And the antiderivative of this gives us 81 over 4 theta, evaluate at 0 and 2 pi. Or this is 81 over 4 times 2 pi minus 0. Or this is just 81 pi over 2. So the difficult part of this calculation is not the evaluations of the integral, it's the conversions from the rectangular coordinate system to polar coordinate system. And remember, the formula have an extra component of r here. So not only you have the surface converted to polar coordinate system, the regions of integrations converting from rectangular coordinate system to polar coordinate system will give you an extra component of r here. So now let's move on to another example.